Welcome back. So, we've fallen in love with orthonormal bases. They're very useful, but every once in a while, you need something that maybe isn't orthonormal, and there are a variety of reasons for this. We'll run through a few examples as we go along. But what can we do if we want to represent a signal with non-orthonormal bases? Well, we already know that we can use a Gramian and project our signal onto some basis set that maybe doesn't obey orthogonality using this Gramian. But we're going to look at kind of an extension or variation on that today. So we'll start with some set of basis functions. Psi let's do this all the way up to psi n. So we have n, and we're going to right now just talk about Rn, although we can extend this later to other systems. Okay, so we're going to let this be a basis. So we know that they will necessarily be linearly independent. And we can take any x and express it as a sum of these basis functions. Like so. For a given set of alpha sub I, and actually let's go ahead and write that as a vector. So we'll say alpha is equal to the vector alpha 1 up to alpha n. So the question is, how do we compute alpha I? Well, let's go through and write things just a little differently using a linear algebra format that I think will make the whole thing become quite apparent. And that is, since we've expressed alpha sub n's in this big vector, we can also express our psi functions, or vectors rather, into a matrix. And so we'll let it's my attempt at a capital psi. Let's hope this works out. It will have column vectors of our individual basis vectors. And so now we can write this as x is equal to psi alpha. Okay, now since our psi vectors form a basis, therefore they're linearly dependent, then we can find the inverse. Now basically alpha is equal to psi inverse times x. So how do we interpret this? Well, this essentially means that we have this nice little reproducing formula that x is equal to psi times psi inverse times x. Well, that's not a really big surprise. We could have guessed that just by the definition of the inverse of a matrix. But this means we can write this in this format. N is equal to 1 to n. And the first product over on the right is equivalent to, for each row, finding this inner product. Okay, so guess I've introduced a new term here. Let's take care of that one too. We're going to say that psi inverse is equal to psi tilde transpose 1 up to psi tilde transpose n, and these are row vectors, so that means that psi tilde n transpose is the nth row of the matrix psi inverse. Okay, so in other words, right here we're projecting x onto this psi inverse, and then we're building up x again using the psi functions. So when we had an orthonormal basis, psi inverse is just equal to psi, and everything was great. But here we have two different functions operating. So in summary, our transform, in other words, if we think of this in terms of the transform being projection onto our basis function, that's also known as the analysis step, is computing alpha n is equal to the projection of x onto psi tilde of n for all of these 1 through n, and the inverse transform, also known as the synthesis, step or stage, reconstructs x psi of n. Okay, so this is really, I think, fascinating. We project it onto one basis, but we reconstruct using a different one. And so we call the psi n tilde as the dual basis. And the dual basis has some nice little properties. mainly because of how it's constructed. This is always going to be 1 for n equals to L, and 0 for n not equal to L. Just from the fact that psi inverse equals I. So, dual basis, and when we consider both of these together, basically are psi n and psi tilde of n. We call these biorthogonal bases. Okay. So this, I'm not sure we have. Good. So let me introduce next the concept of bases for subspaces of Rn, and then we can, I'll give some examples that we can work from. So we have bases for so that's the thing, I guess. All right. So suppose we have T is an n-dimensional where m is less than n subspace of Rn, and we have a basis for that set. The elements of T. Okay. So this is very similar to, but slightly different from what we had before. Now we'll have our capital psi matrix is equal to the matrix made up of the column vectors here, like that. So the problem is, this is n by m, n rows and m columns. It's not square and it's not invertible. But since the columns are linearly independent, it does have a left inverse. So let's see how we would deal with this. If we had, say, given x in T, we know there exists a set of coefficients that will reconstruct x. And there's going to be m of them. So how do we get at the reproducing formula here? Since the left inverse exists, um, we can state that x is equal to psi transpose psi inverse psi transpose times x. Okay, so this matrix here is invertible. Because of the linearly independent columns. And we can now write x equal to the sum m equals 1 to capital M, x projected onto, or the inner product rather, with psi tilde of little m, psi of m. So just like before, but we need to define psi tilde. Psi tilde of m transpose equals the mth row of this crazy matrix, psi transpose psi inverse psi transpose. Okay, so when m equals n, then this whole expression here becomes just psi inverse, as we had before. So now we've got biorthogonal subspaces as well. So, an example of a matrix like this in sorry, my tablet isn't responding quite right. Okay, I'm back. So, an example would be, let's assume we had a basis that was psi 1, 1, 1, 1, psi 2, 0, 1, 1, and psi 3 is equal to 0, 0, 1. We put this into a matrix and find the inverse, and that would give us psi inverse is equal to 1, 0, 0, negative 1, 1, 0, and 0, negative 1, 1. So now, taking the rows of psi inverse to be our psi tilde transposes, that would give us psi 1 tilde is equal to 1, 0, 0. Psi 2 tilde minus 1, 1, 0. And psi 3 tilde 0, minus 1, 1. And we can see that psi 1 with, say, psi 2, psi 3, or psi 4, or psi 1, psi 2, or psi 3, this is equal to 3. Psi 1 with psi 2 is equal to 2, and so on. So we don't have orthogonality, or orthonormality. However, we have biorthogonality. Tilde is equal to 1. Psi 2 with psi 2 tilde is equal to 1. And I'm not going to go through all of them, but just a few examples. Psi 1 with psi 2 tilde is equal to 0. Psi 2 with psi 1 tilde, psi 2 with psi 1 tilde is equal to 0, and so forth. So we have our biorthogonality.